In the last lecture, we have established that any reversible thermodynamic path can be replaced by a zigzag path consisting of two reversible adiabatic and one reversible isothermal process. This replacement would be such that the heat transfer in the original process will be equal to the heat transfer in the isothermal process. Now let's imply this particular discovery from our previous lecture. Let's understand the Clausius theorem on the basis of it. As you can see here, it's a PV diagram in which a particular process is given, a reversible process, but in a very erratic fashion, because this is what actual process looks like. Now the black color lines that you are seeing are the reversible adiabatic processes. So these lines represents a reversible adiabatic process. And the red color lines are the reversible isothermal process, which are joining two consecutive reversible adiabatic process. Right? Now, as per as the definition, the discovery that we have made, the heat that is added to the reversible isotherm process is equal to the heat transfer of that zigzag path. That means the path that you can see here, let's zoom in and see the path that you can see here, this one, and this one, that would be equal to one process. And the same goes for the downward portion also, here, here and here, right? Now if you pay close attention here, you will identify that this whole system, this whole process, this whole cycle inside this elemental strip, it's nothing but the Carnot cycle. That means two reversible adiabatic processes as well as two reversible isotherm processes and the consequent heat addition and a heat rejection. So for this particular elemental strip, let's say this one, the thermal efficiency would be given by what? 1 minus the heat rejected by the heat added, that is Q rejected upon Q added, and that would be equal to 1 minus temperature at rejection and the temperature at addition, that is equal to 1 minus T2 by T1, or we can write 1 minus dQ by dQ2 by dQ1 is equal to 1 minus T2 by T1 as far as the elemental portion is concerned, right? Now this implies that dQ2 by dQ1 is equal to T2 by T1, or we can write dQ2 by T2 is equal to dQ1 by T1. Now if you see closely, the heat rejection is taking place here. Let's see it again. Heat rejection is taking place here for this particular elemental strip, and that is we are denoting it with dQ2. So as per as the sign convention of heat transfer is concerned, heat rejected from the system is taken as what? Negative. So let's put the sign convention here. So it would be minus dQ2 by T2 is equal to dQ1 by T1, or we can write dQ1 by T1 plus dQ2 by T2 is equal to 0, and this is for the first elementary Carnot cycle for this particular elementary strip, right? So similarly there would be n numbers of elementary strips, that means dQ3 by T3 plus dQ4 by T4 is equal to 0, and dQ4 by T4 plus dQ5 by T5 is equal to 0, and so on up to dQn minus 1 by Tn minus 1 plus dQn by Tn is equal to 0. So if we add all of it, what we get? dQ1 by T1 plus dQ2 by T2 plus dQ3 by T3 up to when dQn by Tn is equal to 0. So this gives cyclic integral for reversible process dQ by T is equal to 0. This is your Clausius theorem, and this concludes the theoretical portion of the entropy. Thank you so much for your time, your patience and hard work. And in the coming future, I might add certain more tutorials, certain more lectures regarding entropy section and even more. Thank you so much. It's been a pleasure.